We're going to talk today about two things. One is stress corrosion cracking, otherwise known as SCC, and the other one is hydrogen embrittlement. And the reason I'm talking about both of these together is because one is dependent on the other. So stress corrosion cracking is a failure mechanism, and hydrogen embrittlement is a cause of the failure. So that's why we're doing both of them together. So what's important to understand is that in many industrial accidents and failures, there are problems with metals cracking. Here's an example of a tank failure. This is a steel object that quite clearly has a crack going all the way through it. And this is due to a phenomenon known as stress corrosion cracking. So it's so important that you need to know about it in a course on corrosion. This is, it can be catastrophic, it has to be said. There have been many failures in industrial plants over the years, over decades even, where stress corrosion has happened or occurred, but people didn't realize it at the time, and therefore the accident happened. And it's very often caused by something called hydrogen embrittlement. So we'll say quite a lot of about that today. Let's have a look at one or two more examples. This is the Silver Bridge disaster that happened in the USA in 1967. On the right-hand side, you can see a painting of the bridge just before it was opened. And this is what happened. It took about 20 years for this to happen, but there was hydrogen embrittlement and the entire bridge structure collapsed. Here's another one. This is the Flixborough chemical plant disaster that happened in the UK in 1974. I actually remember this because I was in high school when this happened. And at the time, this was one of the largest explosions ever to happen in Europe. In fact, the blast was so big, it could be heard several hundred miles away on the Dutch and Belgian coastline, completely destroyed the entire factory, and entirely due to stress corrosion cracking and hydrogen embrittlement. So what we're looking at really here are cracks, generally in pipes, always in a situation where you have stress, where the component is either being stretched or it's being under high pressure. And it usually takes place over several years. So you don't normally see the effect immediately, which is the reason why these accidents happen in the first place, because if you don't do careful maintenance and control, you won't notice the problem until it's too late. And it's particularly popular or common to see in pipe failures. So pipes like these ones I'm showing you often have cracks going like this, and they can just burst open and have terrible consequences when it does happen. Here's another example. Again, it's a pipe. It's a brass pipe this time. That's an alloy of copper and zinc. And you can see it's fractured all the way down. This is fairly typical that you get the crack going down the axis of the pipe as opposed to going across it, which happens less frequently, but this is very commonly observed, or due to stress corrosion cracking. Here's yet another example. You can see these fissure lines here going right across this piece of metal. You can see a void space here, which has got something to do with it. And there's a weldment as well. You can see there's a weldment. So metals which are welded, heat treated, they become harder. The harder the material is, the more susceptible it is going to be to stress corrosion cracking. And this word susceptibility is a very important term, because when you actually heat treat a piece of metal like this has been, because it's been welded, then you sensitize the grains within the structure, and those sensitized grains become more brittle and much more likely to suffer cracking like this. So you need to know something about the material science in order to avoid this problem, and also to know what the problem actually is in the first place. So let's look at these bubbles. There are three of them. And in the middle, we have stress corrosion cracking, SCC for short, stress corrosion cracking. Okay. So the things that lead up to a situation where you can get stress corrosion cracking are one, stress. You need stress. That means you have to apply a force to something. The pipe has to be under pressure, for example, or it has to be stretched, or it has to be bent. So stress is obviously important because it says stress corrosion there, so stress is important. The material itself is important. Not all materials will suffer from stress corrosion cracking. Some do and some don't. In particular, high strength steels certainly do. So if you've got a high strength steel, then you will need to be very careful, because that is very susceptible to stress corrosion cracking. So too is brass, and so too is titanium, and even aluminium. So most metals are in fact susceptible to stress corrosion cracking. Obviously, if it's a composite or a plastic, it's not going to be, but we're talking about metals in this course most of the time. And the third bubble is the environment itself. What are you exposing the material to? And it could be seawater, for example. It could be high temperature, for example. It could be a corrosive gas like chlorine gas, for example. Remember, with stainless steel in particular, chlorine and chloride are very aggressive. So you can be certain that if the environment contains chlorine or chloride ions, and you have the stainless steel or high tensile steel under stress, you're almost certainly going to have the conditions where you'll get stress corrosion cracking occurring. So you have to be very, very careful when you design such components that you avoid the problem, or at least you know about it beforehand and do something about it. Look at this slightly differently. Here's a stress corrosion crack in the middle where the circles overlap. So we can have tensile stress. That generally means the material is being stretched. And metals don't like to be stretched too much because they will yield. If they're ductile, that's not a problem. But if they're brittle, then it's a serious problem. If the material is susceptible, and I just mentioned that if I just go back to this example, this is susceptible because it's been heat treated. It sensitizes the grains in the microstructure and it becomes a susceptible material. That will be typically stainless steel, especially if it's been welded, or titanium or aluminium. And like I just said, you need a corrosive environment. In particular, is the oxygen there? Is it acidic? Does it contain chloride ions? Is it high temperature? Does it contain chlorine gas or any other chemicals that are corrosive for that matter? So generally what happens is, here's the metal itself, and you're generally pulling the sample. So it says a tensile stress here. So imagine this is a sample that's being stretched in this direction. And the interface with the environment is up here. And in this particular case, we have an active electrolyte, which in this case is sodium sulfate. This is a light blue area here. So this is the electrolyte, which is the aggressive environment, if you like, the corrosive environment. And we have some oxides, dissolved oxide, it says. And we have some, in this case, it's nickel cobalt oxide on the surface. It doesn't matter what those are in this case. I'm just explaining the basic principle. And the principle is that when you pull the sample in both directions and you start to get a defect, let's say this is a pit forming, you're going to get a stress concentration right here where that black line is there. And this is the initiation of a crack. Initiation of a crack. This term crack initiation or initiation of a crack is a technical term describing what I'm showing you. It's the initial formation of a crack. It's so small, you can't actually see it. And I'm just showing you one, but there may be thousands of these all over the surface. It's not just one. And what will happen then is this electrolyte over a period of time will start to eat into the crack, and it will become this shape. You get a sort of a knot shape, a V shape like this, where the electrolyte is starting to dig into the surface of the, just make it a bit bigger there, it's starting to dig into the surface of the material. And the tip here is where all the stress is concentrated, because it's a very small surface area. So there's a lot of force here, in other words, or a lot of pressure, depending on how you look at it. And this is just going to grow or propagate. And eventually this crack will go all the way through the material and it'll break in half, especially if you have a large amount of stress. The only way you could avoid that is to take the stress away completely. But this doesn't very often happen in practice. So here again, we have this sort of V shape. This diagram is showing the individual atoms or grains. And you've got some metal ions here. This is actually showing the defect chemistry, to be very precise. So you've got some vacancies, you've got some metal atoms, and you've got a contaminant. So it says chloride ion, for example. which is highly aggressive, as you already know. And this is the tip here of the crack here. And this will just go propagate. And what you're actually doing is you're pulling apart the atoms. You're creating a void here, which is the crack itself. And the atoms are just moving sideways. And then the process is being oxidized, contaminants are absorbing, and it just aggravates the whole thing and accelerates it. And it's eventually the crack just whizzes off and breaks the sample clean in half. Here's the same idea again. You've seen this sort of diagram before because this is a kind of rusting process. This is obviously a steel sample because you've got Fe2O3 form. This is normal ferric oxide. This is the intermediate oxide. This is magnetite, I explained to you last week. This Fe3O4 is the mixed oxide of iron containing iron 2+ and iron 3+ cations. And this is iron 3+, Fe3+. In other words, this is the normal rust oxide, ferric oxide in other words. And these then can form inside the crack. You've got the tensile force going like this. And you've got the crack tip is advancing. So the crack therefore is growing down like this. And another thing to say is that when we get the corrosion product inside the crack, it tends to have a larger volume than the original material. So it can even push more the piece apart, so increases the stress. Now let's say something about hydrogen embrittlement. Hydrogen embrittlement is a consequence of the cathodic process that goes on in a corroding system, especially if it's steel, and especially if it happens to be a high strength steel or high tensile steel, or even just a carbon steel. It's less important with stainless steel, it has to be said, but nonetheless it is still important with stainless steel, but it's very much more important with high tensile steel or high strength steel. So what happens is you get this reaction happening on the cathode. You get protons. If it's, let's say you have an acidic medium, so you got a lot of protons around, then they will pick up an electron in the cathodic reaction and form hydrogen atoms. And then these will go on then to form hydrogen molecules or molecular hydrogen. And both the atomic hydrogen and the molecular hydrogen are the cause of hydrogen embrittlement, because what happens is we get the hydrogen evolution is gas bubbles. So most of the H2 comes off as gas bubble, actually. And you can see sometimes gas evolving from the surface of your material if reaction's quite fast. But the dangerous thing actually is the hydrogen atoms. This reaction here, the first one, this atomic hydrogen actually gets absorbed by the metal itself. The atoms inside the steel absorb the hydrogen and they make hydrides. And these hydrides, or this absorbed hydrogen, is the cause of cracking. And it is the cause of the material getting harder and therefore more brittle. So this word embrittlement really means that we are increasing the brittleness of the metal. So supposing it's quite ductile to start with, meaning that we can bend it easily, and we expose it to an environment which has protons in it. Let's say it's a slightly acidic environment. It's acid, for example. And we have stress pulling the sample in both directions, up and down. And we start to get a defect, which becomes the tip of the crack. And here's the very tip here. Then this hydrogen that's formed here, especially the atomic hydrogen, less so the molecular hydrogen, but mostly this one, it gets into the tip of the crack and it goes into the metal directly. And it diffuses all inside the metal surface. It goes everywhere inside the metal. And in particular, it goes down the grain boundaries. And this causes the metal to change its physical properties in such a way that it loses its ductility and it no longer can be bent. Instead, it becomes brittle. And any material that's brittle, that's under stress, will crack and fail. So now you can see the link between hydrogen production, embrittlement, and stress corrosion cracking. All the things are linked together. So that's why we're treating them together. Just for the sake of completeness, by the way, the anodic reaction in this case is iron dissolving to form Fe2+. So that's going off into solution. So this isn't the problem, but this is. the formation of hydrogen, in particular atomic hydrogen. So we need to avoid this if possible. If we have a structure which is being stressed, we want to make sure we don't do this. So we have to find ways not to avoid it, in fact. So if you look under the microscope and you're stressing the sample and you have corrosion under the microscope, you'll start to see what looks like a Christmas tree effect or forked lightning. These cracks are going everywhere from the surface. These propagate. And in particular, what happens is the crack goes down the grain boundaries like this. So here's the grain. You've seen these grains before. All materials have grains in them. And the aggressive environment, or the crack, just propagates between the grains usually, down there, which is the path of least resistance. And the hydrogen I just mentioned goes down this crack as well. It gets absorbed by the grain itself, and the grain changes its properties. It becomes more brittle, less ductile, and therefore it just makes it more easy for the crack to grow even faster. So this is a breakaway situation. It's a vicious circle, if you like, and therefore a runaway situation. Catalytic, you can call it anything you want, self-accelerating. It goes out of control, in other words. It's particularly the problem with a pipe, because pipes they're circular, obviously in cross-section, and they have a certain wall thickness, which might be quite thin. And the inside is very often pressurized, and it might also be at a high temperature, for example, a steam pipe. This one says 1900 K on it. It's quite hot, and here we have 800 K, so this is quite hot. And what happens is when the pipe is stressed the way I've just described, it has something called hoop stress in it, which means the stress is going around the whole circle of the pipe, and it's trying to push itself out. It's trying to expand in this direction all the time. So it's trying to burst, in other words. And the only reason that it doesn't do is because it's designed that the wall thickness and the strength of the material should be able to withstand the force or the pressure inside it. And that's normally okay, up until the point you start to get these defects forming here. And once you reach that point there, then you're almost certainly going to have a failure at some point. Simply a question of waiting long enough for it to happen. It might be years, it might be 20 years or so, but you can be sure it will eventually break. And it needs to break in one place. So let's say this fissure grows more than these ones. This will just propagate and just crack straight, and the pipe will burst at that point. And most likely what it will do is go like this. So it probably started then, it just propagates down in this direction in this case, or it might even do this, okay? Or it might just explode into thousands of pieces. So let's have a look at some micrographs. Under the electron microscope or even an optical microscope, you'll see this effect. You can see the cracks. These dark lines are indeed the cracks between the grains. These are the grains. You can see the grains, and these are the cracks, the darker of the line. This looks like a river flowing through a valley. It almost looks like a satellite photograph of the Earth, actually. But it's not. This is a microscope picture. And you can see the cracks here, and you can see they're following the grain boundaries if you look carefully enough. And this is in stainless steel, and it's been caused by chloride ions. So I think I've already mentioned to you, I think you know this already now, that stainless steel is very susceptible to corrosion by the presence of chloride ion. In particular, if it's stressed like this is, you will get stress corrosion cracking as a result of the attack of chloride ions. So stainless steel is very susceptible to stress corrosion cracking if it's in contact with something aggressive like chloride ions. If it's just in contact with fresh water, it's probably going to be perfectly okay, maybe no problem ever. Or steam, fresh steam, it's probably okay. But the moment you get chloride ion or some other ion in there, then you have the problem. Just to make that clear, so some of these, so this is an electron microscope this time with stress corrosion cracking. And this one, you can see corrosion products have actually got inside the crack here. And here you've got a surface pit, and you've got branched cracks, branched stress corrosion cracking cracks, it says here. And here you've got some very fine cracks. And they, as you go further into the surface, they spread out sideways. This is another one I picked up, just showing the same story again. And this is in magnesium. This is magnesium matrix. It's a magnesium alloy. So magnesium also suffers from this problem. And magnesium reacts with hydrogen to form hydrides. So therefore, magnesium is particularly susceptible to stress corrosion cracking because it very easily reacts with hydrogen. And so therefore, we talk about hydrogen-induced corrosion. So HIC for short. So we have two acronyms. We have SCC, which is stress corrosion cracking, and we have HIC, which is hydrogen-induced corrosion. And the two things are related, as I've just said. One actually causes the other. The hydrogen embrittlement, or the hydrogen-induced corrosion, causes the stress corrosion cracking to occur. And here you can see hydrogen in the, so here's the interior of the material, here's the exterior, got air. Here we got some kind of electrolyte. It says sour acid electrolyte. Don't worry about the word sour. That means it's got hydrogen sulfide in it, to be precise. But the point is it's acidic, so we have plenty of hydrogen ions around, and therefore the hydrogen get inside the metal, and it can form a blister, because when sometimes the hydrogen reacts inside, so you don't necessarily have to have a crack in this case. Hydrogen-induced corrosion doesn't necessarily mean you have to have a crack on the surface, because the hydrogen can diffuse through the metal, and in doing so react with it, especially if it's magnesium. And at some point it can make hydrogen gas, H2 you see there, the little blue bubble. And hydrogen gas, of course, will expand because it's a gas, and it will create a void inside the metal. It will make it blow out, it's form a blister. And eventually that will burst, the hydrogen will come out and it will form water, or react with air to form water. So the mechanism for hydrogen-induced corrosion essentially requires a liquid which contains hydrogen, an acid or electrolyte which is low pH. We have some corrosion on the surface. We form hydrogen atoms which diffuse into the metal. There's these yellow bubbles. And at some point inside the metal, the hydrogen atoms join together to form a hydrogen molecule, which expands inside the body of the metal, causing it to bulge and form a blister. And of course, it will form cracks and lead to stress corrosion cracking. So that is the mechanism for hydrogen-induced corrosion. And it's particularly important in electrolytes which are acidic. And in reality, in the environment, we very often come across something called sour. And sour means it contains hydrogen sulfide here, H2S for short. Oops, sorry, is hydrogen salt. The yellow is sulfur and the red is hydrogen. So H2S is two hydrogen atoms joined to a sulfur atom. And hydrogen sulfide is very common in nature. It happens to occur in the subsoil due to vegetation which is degrading under anaerobic conditions. And that gives rise to sulfide, I should say, hydrogen sulfide gas. So this is the bad smell you can often smell in a boggy area, for example. You know, the smell of bad eggs, in fact. So hydrogen sulfide is formed in nature, and the damage it does is it produces hydrogen easily. And this hydrogen then gets absorbed into the metal along the lines I've just described. And when you get hydrogen gas formed in the body of the metal, it forms a blister, and it can cause stress corrosion cracking to occur. And therefore you get this cone-shaped crack forming. And here's some reactions that we need to consider. So here we have the proton picking up 2 electrons, forming hydrogen gas. The corresponding reaction that you know about is oxygen reduction. Here, oxygen reacting with water to make hydroxide ions. This is the standard cathodic reaction for steel that's rusting. But if we happen to have acid present, such as I just showed here with hydrogen sulfide, then you have to consider this reaction as well, the proton plus electrons making hydrogen gas. So this is the main reaction causing hydrogen embrittlement. And if you look under the microscope at the grains, this is a high magnification electron microscope image. In fact, there are 2 images together here. You can see the grains. I'm just drawing the cursor around a grain here. Here's another one. If you look carefully, there's a crack here, there's a crack here, and another one here, and another one here. And here you see some cracks as well. And here's some cracks. And there are two types of cracks marked on this micrograph. There's one called intergranular crack or crack growth. That's where the crack goes between the grains, which is the most common mechanism because that's the path of least resistance. Now, sometimes you get something called transgranular cracking, where the crack goes through the grain itself from one end to the other, right through the grain. This is less common, but if you're observant enough, you will see it under high magnification like this. So I'm almost done with this side of things. I just want to really get the message home and dry, that you've got to be aware of the fact that once you form a crack, you have an atmosphere inside the crack, which then causes severe stress to build up at the tip of the crack. And this causes the sample or the material to break through embrittlement. And there are various processes you need to know about. You have absorption, you have dissociation, absorption, hydrogen absorbed in particular, you have solid state diffusion, and eventually you get embrittlement. So all of these 5 things you would need to know about. If you want to become an expert, then you need to read about these. I'm just giving you the basics for now. And the solid state diffusion occurs upstream from the tip of the crack. And of course, it happens in corrosion. Obviously, it does. So here we have a corrosion situation. We have an anodic reaction here and a cathodic reaction here. As I just said before, the cathodic reaction we want to avoid is where we get hydrogen evolution formed. And this happens under acidic conditions. So as long as the environment is not acidic, let's say it's alkaline, for example, we shouldn't get the problem with stress corrosion cracking under those conditions because there's no hydrogen, and we certainly won't get any hydrogen embrittlement. But if we talk about neutral and low pH, then the hydrogen embrittlement could be a problem if the metal is susceptible to it. And I've got some more diagrams here. I'm not going to go through all of them in any detail, but you can read this in your own right. It's just here for completeness. And we did this before in a previous lecture, so I'm just giving a link to that one where we looked at cracks and we looked at movement through the grains. This is intergranular crack propagation. And this happens to be in a weldment where we have a large amount of chromium carbide present. Remember what I said about chromium carbide in weldments? Well, that's also susceptible to stress corrosion cracking through intergranular cracking. Here's a case for copper. This is a copper alloy. It would probably be a brass, in fact. And you can see the cracks propagating through the surface. And these are intergranular cracks mostly. And you can see them here again for a aluminium copper alloy. This is a bronze, in fact. It's a copper aluminium bronze alloy.